Hello, everyone. Thank you so much for being here with us today. My name is Duan Chen, and my colleague Christine and I will be presenting our research on predicting pragmatic discourse features in the language of adults with autism spectrum disorder. So firstly, we'd like to provide some background information. Autism spectrum disorder, which we will use ASD as the abbreviation for the rest of the presentation, is a neurological disorder associated with the impairments in communication that can have a lifelong impact on relationships, professional success, and personal independence. Individuals with ASD experience difficulties in social aspect of communication, but the linguistic characteristics associated with those deficits are often difficult to precisely identify and quantify. So one of the challenges clinicians have today is there's no existing tool for quantifying atypicality in discourse and pragmatics. Most previous work on identifying pragmatic features relies on careful manual annotations of transcripts of spontaneous spoken language. However, those annotations are very time-consuming, which makes them very difficult to be applied in the clinical intervention settings. So that's why the ability to automatically identify those features is so important. Also, previous work on computational approach for identifying these features have been focusing on exclusively on the language of children. So we see the opportunity here to explore the language of adults with the ASD. In addition, this prior research has generally been applied to expressive language produced in a semi-structured context with examiner or parent rather than spontaneous conversations with a peer. So the objective of our research here today is that to provide a way to bypass those limitations of using manual annotations and to find a way to label pragmatic features automatically. So to do that, we start from collecting speech data from spontaneously spoken conversations, transcribe and annotate for the pragmatic features we're interested in, and then train machine learning models to predict the features. And lastly, compare results from model prediction with the results from our own annotations.
So first we start by collecting our corpus of spoken language data from spontaneous conversations, and to do so, we gather participants ages 18 to 30 who either have ASD or are typically developing. And we pair up each participant with a conversational partner and have them complete a number of collaborative tasks which require spoken communication in order to draw out the kinds of conversations where we might observe the pragmatic features we're interested in. And the two tasks we focus on in this research are the map task and the island task. So in one of the tasks, the two participants are given a map marked with a red X for where they're located. And the experimental participant, whose map is on the left, and who is either ASD or TD, has to give directions to the conversational partner to lead them to where they themselves are on the map. So they both have maps of the same place, but with small modifications. So there might be a roadblock or missing building names on one map, but not the other. And this task helps us look at how experimental participants communicate with differing sets of information and different perspectives. And then in another task, the two participants are given a hypothetical scenario where they're stranded on an island and they have to agree upon which items they want to have with them. And so they have to choose from a set of items which are given to them and are shown here. So first they just have to choose 3 items to have in general, and then they have to choose 1 item for entertainment, and then finally 1 item to help them escape from the island. This task helps elicit some natural discussion between the participants since they have to exchange opinions on what's important to them and weigh the pros and cons of different options, and then eventually come to an agreement on what to bring. And so after collecting all the spoken data, we annotate the transcripts for pragmatic features. And in particular, we're interested in annotating the politeness, the uncertainty, and the informativeness of each utterance. So to define our features, the politeness of an utterance measures how much it contributes to a polite and collaborative dialogue. The uncertainty features measures the amount of uncertainty the utterance expresses about its correctness. And finally, the informativeness feature measures the amount of specific information content contained in the utterance. So using these definitions, each utterance is then annotated by 1 to 2 human annotators on a categorical scale of 1 to 3, with 1 being the least polite, uncertain, or informative, and 3 being the most, and then 2 being neutral. To evaluate our annotation scheme, we can calculate how often the 2 annotators agreed on a feature's value. And we can also calculate Krippendorff's alpha, which helps us measure inter-annotator reliability. And from this, we can see that we have a fairly high percentage of agreement between the 2 annotators. Here we can see a sample of some utterances from our data set and how they were annotated. In the first one, we see we have a politeness of 3 because the directions we're going to have to go down are phrased using the more inclusive first person plural we, and also padded with a future tense going to. And the second utterance has a politeness of 1 since it's a very direct imperative command. In the sentence after that, we can see an example of high informativeness since the irrigation pond is a proper noun and points to a specific location on the map. And then in the next sentence, we see an example of high uncertainty because it seeks information which cannot be answered with a single word or phrase, but rather requires a longer explanation. And then the sentence after that shows an uncertainty of 2 since it asks a yes/no question and can be answered with a single word response. And so after we have all our data, we want to train some models on our annotations so that we might be able to annotate these pragmatic features automatically and skip the time-consuming annotation process. So we train a model for each feature individually, and we give it the utterance as the input and expect the feature label of 1, 2, or 3 as the output. The text utterances are converted to embeddings for the model, and we've tried a number of different model algorithms embeddings so far, which you can see in the table. Currently, our models predict a label for 1 utterance at a time and don't take the utterances before or after into account, though this might be a good area for us to explore next. And then also to evaluate our models, we test them against a number of baselines. So we have the standard baselines like the majority baseline, which always predicts the majority class, the random baseline, which predicts a random label with an equal chance for each class, and the stratified baseline, which predicts a random label with probabilities corresponding to the distribution of classes in the data set. And along with this, we also look at previous research on the topic and test our data on existing pre-trained models. So we tested it on a pre-trained politeness model, which is an SVM trained on the Stanford politeness corpus, which consists of conversations from Wikipedia and Stack Exchange forums. We also have an existing model for uncertainty, which was trained on the SEGED uncertainty corpus, including annotated sentences from corpora of different genres. And finally, we also have an existing informativeness classifier, which uses logistic regression and is trained on the Squinky corpus, which is annotated for informativeness, implicature, and formality. So using all these baselines, we can better measure how successful our models are.
So we can see here a side-by-side comparison of the baselines we have. For politeness and uncertainty, the majority baseline is the highest. And for informativeness, we have the existing model as the highest baseline. Specifically for politeness, we can see the baselines are really, really high. And this is due to the fact that we have a very uneven distribution of annotation for politeness, as we have much more annotated number 2 as the politeness score versus 1 and 3. And here shows our model results alongside with the best or the highest baseline, shown in the bar of orange, we can see that all models performed better than the baseline across all three features. The sequence model specifically performed well for politeness and informativeness, while the BERT model, which is the green bar here, performed the best across all three features. So we wanted to dive deeper into seeing how well our model captures the group differences, which I mean the autism, people with autism versus people with typical development, to capture their differences as we see in our menu annotations. So we decided to conduct a t-test to measure the significance of results, results from our best model, which is the BERT model. So we can see here in the table for math task, ASD participants are more polite and less informative. And for island task, ASD participants are more uncertain and also more informative. We think this kind of difference may result from the fact that there's a different nature of the task and the roles. So for math task, there's greater opportunity to phrase synthesis politely, while in the island task, there's more exchange of opinion, which we think ASD participants may express more uncertainty in situations involving opinion when providing facts and instructions. So the BERT predictions in here shows here only captures the group differences for some features. Specifically, I want to highlight is in the map task, the politeness feature, and also in the island task, the informativeness feature. Two other quick note is that the BERT model prediction didn't capture statistically significant differences, which means a lower p-value. And also the model didn't capture the variance between the tasks. So these two are the 2 points that we wanted to explore more in our future research.
So in conclusion, we've seen from our research so far that there are quantifiable and significant differences in pragmatic expression between the ASD and TD groups, and those differences may vary depending on the task and context in which the utterances are spoken. And from the results of our models, we see that all our models perform better than the best baselines for each feature, with the BERT model performing the best. And from here, we want to work on getting more data by both leveraging external annotated corpora and collecting more data from new participants. We also want to try different neural network structures and fine-tune our model for capturing those group differences between ASD and TD, which it currently fails to capture. And finally, we also want to experiment with more models and embeddings and look into training a context-dependent model, which takes the surrounding utterances into account. And so, yeah, so thank you so much for watching our presentation, and feel free to contact us with any questions or suggestions.